Hi everybody. Today we're going to do section 11.5 in the attempt apply discrete structures, and that is subgroups. Now, some of you may have taken linear algebra, and you may have learned about vector spaces. And when you have a subset of a vector space, which is itself in its own right a vector space, then you have, for example, we learned that like in R2, a line that goes through the origin is going to be a subspace of the vector space R2. By the way, if you're not familiar with this, don't worry about it. But some of you may have already taken linear algebra and you know what I'm talking about. Anyway, we're going to learn a similar concept today with groups. That if you have a subset of a group, and this subset is itself a group, then it is called a subgroup of the larger group. And of course, condition is that it's the same operation. Otherwise, well, I don't know. Don't make much sense. So let's just here we go. So this is 11.5 subgroups. And as I said, a subgroup is a subset of a group, which is itself a group. Anyways, so we want to concentrate on some of the properties of subgroups. So we want to start with some conditions here, 11.5. So if you want to know if something if a subset is a subgroup, then all you have to do is prove that it's closed under the now notice that G star and H star, it's the same. It has to be the same operation, otherwise it doesn't make any sense to even call it a subgroup. So all you have to know is that it's closed, that it has an identity, it has an inverse. Well, if it has an identity, it has an inverse. That's already two of the three conditions. The only thing left is associativity, and so all we have to do is show. We know we have the identity and the inverse because that's what B and C are saying. All that stuff is associative, and that's simple because since G is a group, the original, the original group is a group. Then associative property holds for all of its elements, but all the elements of H are elements of G, so all the elements of H are associative. So they're associative, and it's of course closed, and its identity inverse got it all. Very simple thing to prove. Let's move on to something more fun. And here we go. Conditions for a subgroup of a finite group. So given that G is a finite group and H is a non-empty subset of G, if H is closed under that then under that operation, then H is a subgroup of G. So as long as, if you have a subset which is closed, that's going to be enough to make it a subgroup. But notice that, again, those of you who took linear algebra, you see how it's very similar to the way it works with vector subspaces. Anyway, I don't want to get too off, to that thing. But anyway, proof. So we want to show that conditions B and C of theorem 11.5.3 follow from the closure. Now, what is conditions B and C? That is that it's closed and that it has an identity, it has inverses. Closed, identity, and inverses. So let's just take a look here. Okay. Well, we know it's closed because that's given. It's given to us as closed. So now we have to show that has. Well, let's just take a look. So we want to show here, our proof is going to show that the identities and the inverses follow from the fact that it's closed, and which was condition A of this 11.5.3 theorem. Anyway, so what we're going to do is we're going to select any element of H, any random element, and we're going to call it beta. And now I'm going to look at the powers of beta. Now, meaning if I multiply beta times itself in that operation. Now, by the way, again, we're looking at this like powers, but the operation could be an operation of addition, but the point is that we're applying that operation to beta over and over, repeatedly. So all of these beta itself, beta times beta, beta to the third, blah, blah, blah. They're all in H. How do I know they're all in H? Because we said that H was closed. That was part of the, getting in my own way here. We said that H was closed. That was part of the conditions here. And so we know that by theorem 11.3.15, and what is that theorem? So let's just take a look. We know that if G is a group and A is an element, there exists a positive number m such that a to the mth power equals e. I mean, if I keep on taking powers of a, eventually I'm going to hit e if it's a finite group, which is what we're dealing with here. Let's go back to 285. 285. Okay. All right. So well, that means that by that theorem means there is an identity element e. What about inverses? Well, if a is equal to e, then a is its own inverse. And if a does not equal e, that means a to the q power does equal e. For some number q, which is between 2 and the order of g. Now, if e is equal to e to the q, so e to the q minus 1 times a is equal to e, which means a inverse is equal to a to the q minus 1, and pound. So it's shown that any random element a has an inverse, which is a to the q minus 1, and there we go. So we've shown that there's just given that this finite group is given that this finite subset is closed, that makes it, or the subset of the finite group is closed, that makes it forces us to have an identity, that forces us to have a inverses. So really, that's all we need, is that it's closed. Once it's closed, you got it all. That's what this theorem is saying here. That any subset, any closed subset of a finite group is in itself a subgroup. Okay. Of course, H has to be a non-empty subset. Well, it's kind of, what's the fun is it anyway? Okay. This is kind of interesting. Is 0, 5, 10 or 0, 4, 8, are they subgroups of Z15? Let's look at a similar kind of example. Let's go to Z12. Z12, and we're gonna do I guess we'll do addition. And now let's look at I don't know, 0, 3, 6, not, oops. We're over here, 3, 6, 9. Okay. And here we're gonna go to 0, 3, 6, 9. And we're going to okay, so now let's now again, our operation here is addition. It's not, our operation here is addition. So for addition, it's 0. Oh, I don't want that. in my own way here. It's getting very annoying here. Okay. 3, 6, 9. Now 3 plus 3 is 6. 3 plus 6 is 9. 3 plus 9 is 12. 12 is the same thing as 0. Of course, again, we have this. Now, 6 plus 6 is 12, which is 0, and 6 plus 9 is 15, which is 3. That's 3. And 9 plus 9 is 18, which is the same thing as 6. So let's just highlight this yellow. That's what I want. All right. So again, this is a group because we have 0, which is the identity element. There's a 0. We get that Sudoku-like 0 thing. There's a 0 in every column and a 0 in every row. So the inverse of 0 is 0. The inverse of 9 is 3. The inverse of 6 is 6, and the inverse of 3 is 3. And that's kind of cool. And 0 is the identity element. Every element has an inverse, and we're good to go. Let's just wrap this up sort of. There you go. And I'm going to put this in the Google Doc, so you have it forever for posterity. So you see here that let's see the scroll. So Z12 under addition. Z12 under addition, or I should say, the set 0, 3, 6, 9. Is a subgroup of Z plus. And that's all I'm trying to say. Okay, let's go back to our textbook. And let's go on to the next thing here. Now, the next thing is something called a cyclic subgroup. And this is a particular type of subgroup. It's a special type. And really, because it's so simple, it's such a simple one. And it's called a cyclic subgroup. And basically, it's formed by the powers of a certain element. So G is a group. A is an element of G. Cyclic subgroup generated by A, and we write it this way, A with the little bracket thingies, is the set of all powers of A, where N is any integer. So if we look at all the powers of A, so sometimes, not all the time, but sometimes the powers, if I look at all the powers of A, that's going to form a group in its own right. That's just going to, now I'm not saying it's always going to happen, but if it does, then that group is a subgroup of G, because A is some element of G, and is called a cyclic subgroup of G. And we say that A is the generator of the subgroup, which makes sense because this all came from powers of A. So let's get some definitions under our belts. So if G is cyclic, then that means there exists a beta such that the beta generates G, which means the powers of beta form all of G. So that means G is a cyclic, which means, right, G itself could be the cyclic subgroup. Now, of course, when I talk about powers could just mean, adding it, multiple times. Okay, so you gotta use that idea. The order of a group element. So the order of an element A of a group G is the number of elements in the cyclic subgroup of G generated by A. Meaning how much. So when I keep on taking powers of A, how many powers of A would it take to get to be generated by that group? How do I say this? What's a good example of this? I'll give you an example of this in a minute. Well, let's look at here. We have the real numbers with multiplication. I'm looking at all the powers of 2. That's Z. So it's positive and negative. So if I look at all the powers of 2, I get 2, 4, 6, 8, 2, 4, 8, 16, 1, 1/2, 1/4. These are all powers of positive and negative. Notice it's infinite because and I specific, but here it doesn't have to be finite. So, before we did a theorem about finite, groups and subgroups, but here it doesn't have to be finite. Anyway, this is a subgroup because it's closed. If I multiply any power of 2 times another power of 2, the result will be a power of 2. There's an identity element, which is 1. Any element has an inverse. 16 has 1/16. 1/4 has 4. Every element, 1 has itself. Every element does have an inverse. It's closed. It's I would say associative because multiplication in the real numbers is associative, and there's identity. So we got it all. If you look at Z15, so if you look at the numbers generated by 6, you get 0, 3, 6, 9, 12. Why is that? Because 6, again, it doesn't say, are we doing addition here or doing positive powers? Multiples of A, positive powers. Okay. Is it saying here what it is? The identity to obtain all of A. The multiples of 6 are 12, 3, 6. Multiples there's also 3. I'll just show this we can have different generator. So this is interesting because if I look at all the multiples of 6, if 6 itself, 6 times 1, 6 times 2 is 12. 6 times 3 is 6 times 3 is 18, but 18 is 3, mod 15. 6 times 4 is 24, but 24 is 9 mod 16. 6 times 5 is 30, but 30 is coming to 6 mod 12 mod 15. 30 is coming to 0 mod 15, and then we go around the whole gamut. If I look at all the powers, all the multiples of 3 or of 9 or of 12, I'm going to get the same group. But I also wanted to make a point that if I look at the, just think for example here, suppose I look at this here. I'm going to actually draw this in. So suppose I want to look at 5 in this. Well, the multiples of 5, well, mod 15. So this 5. 5 times 2 is 10. 5 times 3 is 15. 15 is the same thing as 0. And then that's it, we're done. And 5 times 4 is 20, which is back to 5. So my point is that if I look at this, so the point is that, oh, I want to get rid of that. My point is that, oops, I just lost it. There was a word I wanted here. So notice that in Z15, not every element has the same order, because the order of 6 is 1, 2, 3, 4, 5. There's 5 elements here. The order of 5 is only 3. So 6, 9, 12. These make 5 element subgroups, whereas this only makes a 3 element subgroup. Well, you notice that 5 and 3 both go into 15, and that is not a coincidence already. Well, let's see. Is there anything else? Finally, if A is an element of a group, then the group generated by A is going to be the same as the group generated by A inverse. And an easy way to see this is that 9 is and 6 generate the same thing. But also, you know, this is all the integral powers of A, and that's all the integral powers of A inverse. But basically, the powers of A are positive powers and negative powers. The positive powers of A are the negative powers of A inverse. The negative powers of A are the positive powers of A inverse. They're basically the same thing. So this theorem is really very simple to see and to prove. And we are done. Well, that's it. How do you like that? We did 11.5. I think it's fabulous. We're going to stop the stop the recording. And that's it. Bye, everybody.